Okay. Hi, everybody. Let's get started. Last time we learned about how to analyze the work span and parallelism of recursive programs, recursive parallel programs. And today we're going to look at a few more analyses of parallel programs. And we're going to focus on merge sort, which is one of the simplest optimal algorithms for sorting in serial. And you should, I imagine, be familiar with this algorithm from your prerequisites. Here is the basic algorithm in C. Unlike quicksort or insertion sort, merge sort does not rearrange the elements in place, but requires extra storage. But among so-called comparison sorts, which are algorithms that sort by making comparisons between elements, not like counting sort or radix sort, merge sort is asymptotically optimal, running in order n log n time. So let's take a look at what the code does. So the merge sort function takes as input a presumably unsorted input array A of n elements and sorts them into increasing order, putting the result into B. Now, the restrict keywords allow the compiler to optimize better because it knows that the two arrays A and B won't overlap. Otherwise, it would worry that changing an element of one of them might affect the other. So that's what restrict does, is it allows you to tell the compiler that not to worry about making the code correct for the case where A and B might overlap. Might be, elements of A could be elements of B or whatever. Now, when passing arrays in high-level languages, the length of the array often gets packaged with the array, okay? But this is not the way it works in C. So in C, it treats the array as a pointer to the first element, and you've got to pass the array size, as a parameter on its own, because C won't track it for you and keep it associated. Okay, this is one place in my experience where software discipline can help you keep things organized so that your coding team won't get confused by each other. So for this code that I'm going to talk about today, there's the methodology that the size parameter is always passed as a parameter immediately after the array. For arguments that come later, the array size might be omitted if it's implied by something earlier. Okay, so if we have an array A, so in this case, we have an array A, it has length n, and it's followed by B, which also turns out to have length n, but that's implied. Okay? So that's just a methodology that that we adopt, and it helps keep the code organized and helps make it easy to communicate and not get confused and such. And I hope I haven't violated that anywhere. Okay. Now, the assert here is a good programming practice. We first check that we're passed a legal positive value for the number of elements. There's no overhead to an assert at runtime unless you run with asserts enabled at runtime. Usually you don't. Now, this is a recursive algorithm, and for the base case of the recursion, we have a one-element array. Well, a one-element array is already sorted, so we just copy the element to the output. For a high-performing algorithm, you would probably want to coarsen the recursion to avoid function call overhead and write a carefully coded function for small n. But we're going to do an easy version so that we can, we don't have all those programming complications to make the code more complicated. It's always the case. You want it to be higher performing, the code tends to get more complicated. Not always. So when it actually gets simpler and it's higher performing, that's what we really cherish. Okay, so now we're handling the general case when we have more than one element. And the first thing that we do is allocate a temporary array C on the stack. Now, different compilers, you should just be aware of this because this is something that may even change soon. Different compilers handle stack allocation of this array C differently. Okay, I guess here I have two C's going on. I've got C the language and C the array. So I'll try to make sure I disambiguate. So most C compilers, there's compilers for the language C, place the entire array C directly on the call stack. But as I mentioned, that may change. There are discussions that LLVM may soon malloc C and only put a pointer to it in the stack frame, remembering to free the array storage when the stack frame is popped. Okay, you won't be able to see a difference from, it doesn't change the language at all. It's just the way they implement it under the covers. Having only a pointer to the array ensures constant size stack frames, which has performance advantages in the manipulation of the stack. It does take an extra dereference to get the start of the stack. You have to index the stack to get the pointer and then index off the pointer, rather than just indexing off the start of the array. So if it's embedded in the current frame, it can go straight to the index off of wherever the array is, rather than first dereferencing a pointer to it. But since modern compilers do a great job on common subexpression elimination, that extra dereference is usually avoided, and so that's kind of the rationale for why they are looking at that. Now, the OpenSilk compiler is based on LLVM, so it does whatever LLVM does, which for now is stack allocating the array C. It puts it actually on the call stack. So that's just a little background of something you might be aware of so that you don't think that these things don't change from time to time. Okay, now we recursively sort the first n over 2 elements of A and putting the results in the first n over 2 elements of C. Okay, so we say n over 2, we put it in the first elements. And then we sort the last n minus n over 2, putting the result in the last n minus n over 2 elements of C. Now, when you do n over 2 in C, it rounds the n over 2 towards 0. Okay, so it's basically taking, if n is a positive number, it's taking the floor of n over 2. And so the amount left is the ceiling of n over 2. And I usually write n minus n over 2 rather than ceiling of n over 2, not just because it's much easier to write without calling a math function, but it's now easy to check that the total number of elements in the two calls is n. Okay, we haven't missed an element. Okay, so if I add up n over 2 for the first merge sort, that's how many elements are involved there. In the second merge sort, I'm adding in n minus n over 2. They cancel, and I can see, oh yeah, I've got n elements. Okay, and that's once again, a trick I've learned to do over, with experience to avoid writing programs with bugs, of missing something somewhere. Okay, and the compiler will be smart in how it computes n minus n over 2, using common subexpression elimination and so forth. So I don't worry about that costing me extra work in any way. I'm also using a heavily used trick that works in C, but not in most, I guess, other programming languages. In some languages, to denote a subarray, you have to pass an array, a lower bound, and a length, okay, or a lower bound and an upper bound. You can pick which one you want to do. They do it differently. But in C, you usually only need to pass the start of the subarray and a length, okay? And so in this code, instead of passing the address of the starting element of the upper half of A, So the way it works is that a subarray is just a pointer to the first element. And so if you're going to have a lower bound and an upper bound, well, don't bother with the lower bound and upper bound. Just start your array at the first element. Okay. So in this code, instead of passing the address of the starting element of the upper half of A as ampersand A of n over 2, okay, we've passed the location with a few fewer keystrokes as just A plus n over 2. And similarly for the upper half of C. Okay, the two methods are equivalent, whether you pass ampersand A of n over 2 or A plus n over 2. Okay, the compiler produces the same optimized code. There's no difference. Okay, as we discussed in lecture 9, and I'm sure you know from project 1, the subarray tricks gets more complicated for multidimensional arrays, but we don't have that here. Okay, for multidimensional arrays, the problem is that when you have a submatrix, it's not contiguous in the outer matrix. But for one-dimensional arrays, it is contiguous, and you can use this trick. And you'll see it all over the place in C code. Okay, so finally, the last step of merge sort is to call the function merge, which merges the two sorted arrays in C into the output B. Okay, so any questions about, we're going to see the code for that in just a minute, but are there any questions about the merge sort routine? I think you've probably seen this, but you know, whenever you code stuff up, it depends upon the language what happens, and you know, I just want people to be familiar because we are going to dive into some other codes, and I wanted you to be a little bit familiar with, you know, how my style of coding, just so you can read my stuff better. Okay, it looks like we should move on. Okay, I hope that was pretty much review. We're going to have a lot of review today, but it's going to get really interesting still. Okay, here's the code for the merge subroutine, and here I don't have any code comments, just so that I could keep it compact on the page, okay? I'll let you study the code on your own. Merge is where all the heavy lifting gets done in merge sort, okay? It's in this merge procedure. And so what I'll do here is illustrate how it works, and then you can look at the code and see exactly how it works. Okay, so here we have two input arrays, A and B, of length 4 each, and an output array, C, of length 8. So the code figures sort of where's the minimum element overall in the union of the elements from the two input arrays. Now the two input arrays are sorted. So it's either going to be the first element of A or the first element of B. Okay, that's the assumption that the two input arrays are already sorted. So the code compares those first two elements, and whichever is smaller, in this case the 3 at the start of array A is smaller than the 4 at the start of array B, it moves that element 3 to be the first element of array C. And it also advances the pointer to the first element of A to point now to the second element of A, and it decrements the number of elements in A. Okay, NA is the number of elements in A. Okay, now my animation shows the 3 disappearing from A, but of course the code just copies it from A to C. That's still left there, but it seemed easier to show the animation where you weren't focused on things that had been dealt with. That was my way of sort of saying, okay, this thing's been dealt with. Okay, and now we just do it again. Okay, the minimum this time is B's first element, since 4 is smaller than 12. So it moves the 4 to be the next element of the output, advances B's pointer, and decrements the number of elements in B. Okay, next it moves 12. Okay, now 14. And 19, And it keeps going, 21, okay, 23, and now one of the arrays is empty, okay? And when one of the, in this case it's the B array, okay? And now we finish the first main loop. At this point, one of the last two loops copies whatever remaining elements there might be to the other array. And the other array here is A. So there's only happens to be one more element there, but there could be more than one element. Okay, so 46 in this case gets copied to the output, and we're done. Okay, so what's the time to merge N, which is equal to NA plus NB elements? Well, you should know this. It's order N, because you've seen this before. And the reason is because all three loops have constant time bodies. And each time a loop body is executed, one of the N total elements ends up in the array C. So therefore, there can't be more than order N loop bodies executed. Okay, so that should be review. Now let's take a look at the topic I really want to talk about today, which is parallelizing merge sort. Okay, how can we parallelize this algorithm? Okay, so here's the merge sort. Okay, anybody have any ideas? Want to share on Slack what your ideas are? Okay, what might we do to parallelize this algorithm? Yeah, it's like easy question. Got a lot of answers. Good participation points for all you folks. Okay. So, yeah, do the two recursive calls in parallel. Okay. So, and you can do that by essentially spawning the first merge sort here. Okay. But before we do the merge, we have to put in a sink. Okay. Holy cow, that's all there is to it. We have a parallel merge sort. Okay, this parallel merge sort stuff is easy. No, we don't have a race on C. Good question. We don't have a race on C because the first merge sort is outputting to the first n over 2 elements of C, and the second merge sort is outputting to the last n minus n over 2 elements of C. Okay, so that's like really, really important, okay, that they didn't overlap. Okay, and you know, of course, you would want to check this with Silk Sand so that you made sure that you didn't accidentally overlap something. Okay, that's actually an easy bug to have for something like sorting, because if I happen to sort a few too many elements in the first one or a few too many in the second one, the serial code would still work perfectly right, but you'd have a race. Okay, so this is a classic place that I've seen races come up, is that the two arrays actually overlap, but because you're sorting them, it doesn't matter if you sort in a few elements, the serial code is still perfectly correct, okay, when you run one after the other. Okay, but when you try to do it in parallel, you could get a race. Okay, so can we parallelize the merge itself? We'll get there. Okay, so we want to analyze this, but before we do, let's just visualize how the parallel algorithm works. Okay, so now we have a parallelized merge sort. Okay, so we have actually parallelized it. So here's the here's a little animation. Okay, so we're going to run it on. I shortened up the code to get removing the base case that we have some room, and we're going to operate on this input array. And let's assume, to understand how it works, that we have infinite parallelism. Okay, so we can understand the logical parallelism that we have. Okay, so the first thing that the code does is basically divide the array into two arrays of size n over 2. And then it calls merge sort in parallel on each of those. Now, what's the first thing that those two recursive calls do? Well, they just divide their respective subarrays in two and call merge sort on each of the 4 subarrays of length n over 4. But the first thing that the 4 recursive calls do is divide their respective arrays in two, okay, and call merge sort on subarrays of length n over 8, okay? Now, of course, in practice, it's never going to be this synchronous, okay? You know, it's going to be at different times, in part because we're not dealing with an infinite number of processors, and in part because there can be small execution time differences depending upon what happens in the merge routine, for example, okay? So in this case, the subarrays now all have size n over 8, which happens to be 1 for this example, and the merge sorts return. It returns on the base case initially and calls the merge, and that causes each of the pairs of elements here to be put into sorted order using the merge routine. So we have 19 and 3 becomes 319, 12 and 46 stays 12 and 46, 33 and 4 becomes 4 and 33, and 21 and 14 becomes 14 and 21, okay? And as I say, all of these merges could happen asynchronously. But I'm showing them synchronously with infinite parallelism so you can see the fabulous amount of parallelism the recursion tree can generate, because it's got all those leaves operating at the same time. Okay, so after all those 4 merge sorts that produce the size 2 outputs return, we then can merge those into arrays of subarrays of length n over 2, which is equal to 4. And then, and of course now those subarrays are sorted, and so we can then merge those, and we get that, and we're done. What a simple and great parallel algorithm. Okay, really, really easy to do. Okay, really easy to code. Okay, in fact, before parallel computing became widespread back in the 1970s and 80s, lots of researchers published papers pointing out just how easy it would be to generate vast amounts of parallelism for algorithms such as merge sort and quicksort in this way. Now, of course, that was before the workspan theory of parallelism had been developed, and people just bandied about the term parallelism without really having any idea how to quantify it. Okay, but since we live in a more enlightened age, as evidenced by the current political discourse, let's quantify the amazing amount of parallelism that parallel merge sort can generate in a quantitative way. Okay, so we're going to quantify it in a quantitative way. I guess that's what I said, yes. Okay. We're going to analyze a parallel recursive program. So get out your handy dandy master method cheat sheet if you haven't got it memorized. Okay. You'll definitely want to practice solving recurrences quickly if you want to do well in the quiz, which is in just 2 weeks. So here's the URL at the bottom here so that you can print it out or put it up in another window, because it can't stay here while we move on. And can we, TAs, can we get the URL in the Slack channel? I'll give you all a few moments to copy it. There we go. It's in there. Okay, so it's in the Slack channel. So we'll move on. Okay, good. Okay, let's start with the work. We know we want to analyze work. We want to analyze span. So work. For that, our analysis from last time said we can just look at the serial projection. We don't have to count up things because we know that loops for the work and silk spawn and silk sink don't add any asymptotic overhead. Okay? So we look at the serial projection, and here's a recurrence that describes the work. The recurrence says the following. Okay, to sort an array of size n, we must sort two subarrays of size n over 2, okay, plus perform order n additional work to perform a merge of size n, as well as a constant amount of other bookkeeping, which we can absorb into the big theta. So let's do a Slack poll for which case of the master theorem this is. Okay, we all know the answer. It's n log n, right? But what's the case that we have here? People all think it's case 2 with k equals 0. Oh, now we got a case 2 with k equals 1. Okay, so case 2 with k equals 0 is correct. Okay. Okay, it's case 2. We have A equals 2 and B equals 2. So n log base B of A is n to the log base 2 of 2, which is n to the 1, and that's just n. Now, f of n is order n, theta n, okay, which is the same as theta n log to the 0 n, okay? So we just tack on an extra log, and our answer is theta n log n, okay, just as you were all taught in grade school, you know, or college. Okay, so I hope this is review for everybody. Okay, good. Okay, now let's compute the span. Oh yeah, span. For spans, we like to do span polls. So everybody, please guess the span of the parallel merge sort in the Slack poll. So what do we have? Theta log n, theta n log n. Looks like the log n's have it. Okay, let's solve this and figure it out. Got 1 theta n log n. Good. Okay. Okay. So let's write a recurrence. Okay. So here's the recurrence. Okay. It says that the span to sort an array of size n is the span to sort an array of size n over 2 plus theta n additional cost. So the additional theta n comes from the merge routine plus the constant amount of bookkeeping. So I hope that part is clear. Okay, but why is the coefficient on the t sub infinity n over 2 term 1 when we have 2 recursive calls? Okay, The reason is that the longest path in the underlying trace can only run through one of the recursive calls because they operate in parallel. And it'll run through whichever recursive call or spawn takes longer. Hence, we take the maximum. But the two recursive calls both sort n over 2 elements. So the maximum is t infinity of n over 2, whichever way we go. Okay? So we've got our recurrence, and now we can use the master method. Okay, so let's do a slack poll again. Which case of the master method is this recurrence? Okay, yeah, we got pretty much everybody joining the bandwagon on this. So the correct answer is E. Okay, case 3. Okay, so let's see why and solve the recurrence. Okay, so we have that A. Let me just see here. So we have that A equals 1 and B equals 2. Good. So n to the log base B of A is just n to the log base 2 of 1, which is n to the 0. And n to the 0 is 1. And 1 grows polynomially slower than f of n, which is theta n. So the answer is theta of f of n, which is just theta n. And it turns out the function f of n equals theta n satisfies the regularity condition, which technically you should check, but I'm not going to bother to because everything we see satisfies the regularity condition. Okay, so the answer is theta of n for the span. Okay, so you can compare that with your guess. So if you look at the parallelism of merge sort now, we have of parallel merge sort, we have the work and span, and the parallelism is the work is n log n, the span is theta n, and so the parallelism is just the ratio, which is theta log n. Now you may recall that we have a technical name for parallelism of this nature. Okay, does anybody remember the technical name for this kind of parallelism? So answer in the Slack poll, and not Slack poll, answer in Slack. What do we call this kind of parallelism? Yeah, we call it puny parallelism. Puny parallelism, okay? Wait a minute. I thought we had all this fabulous parallelism. We had n leaves going. Order log n is just not very much parallelism, okay? So you can see the advantage of being able to quantify parallelism rather than just hand-waving about it, okay? Some very smart people thought this algorithm had lots of parallelism, okay, that, you know, in the early days, okay? But we can be smarter because we've got history behind us, okay? So let's try to salvage parallel merge sort, okay? So does anyone have any ideas as to where in the code we should focus our efforts? Please answer in the Slack. Where should we focus our efforts? Yeah, obviously from this analysis, we can see that we need to parallelize the merge, okay? Okay, the merge is the bottleneck. But if you think about it, that looks tricky because the serial merge algorithm that we did looked awfully serial. Okay, it was not only a serial algorithm, it looked serial. Okay, it wasn't divide and conquer anything. We're just picking from the front of each of the arrays. And it's super simple code, so it runs really fast. You know, serially it runs really fast. But it looks kind of inherently serial. So I wonder what algorithmic strategy we might use. Does anyone have any idea? Please suggest an algorithmic strategy in Slack. What algorithmic strategy might we use here? Okay, divide and conquer, front and back at the same time. Merge isn't exactly oh, that's probably from the previous question. Okay, what strategy, algorithmic strategy? Coarsening recursion, order one median finding, two pointers, two finger. Okay. So the strategy we're going to use is divide and conquer. Okay. The strategy we're going to use is divide and conquer. And, you know, the way you're answering forces me to give you a piece of advice that you will carry you well all the way into old age, you know, or at least through a job interview. Okay, so here's the piece of advice. When someone asks you for an algorithmic strategy and you're clueless, guess, divide, and conquer, even if you don't understand the problem, because that's usually the answer. Okay? Well, you could say dynamic programming, okay, because that's the other one that comes up. But guess one of those, okay, and divide and conquer happens more because there aren't a lot more algorithmic strategies to choose from. Okay, and when you do it, say it in a thoughtful way. You know, say something like divide and conquer. Okay, as if you've given it due consideration. Okay, so listen to me and you'll go far. Okay, look where it got me. I'm a professor at MIT. Okay, moving along. Okay, so let's see how to design a parallel merge using divide and conquer. So suppose we have two sorted arrays, A and B, that we want to merge. Now they might not be the same size. So here I've got A having NA elements and B having NB elements. And let's assume that NA is the larger of NA and NB. So NA is greater than or equal to NB. So the first step of our divide and conquer is to choose a pivot, which we'll choose as the middle element of A, okay, which is to say it's the median of A. Okay, so let's call its index MA for median of A. Okay, I'm not really talking about my mother. Okay, now if I were really coding this, I'd probably call the variable something like median of A. But when you make PowerPoint slides, sometimes you have to compromise. But if you end up compromising in the code you're writing and you write these really short variable names, your teammates won't be able to understand what you're doing. Okay. Now, all the elements in A to the left of the index of the median are less than or equal to the median itself. A of M of A is the pivot. The median that we're going to call the pivot, A of M of A, because A is sorted, okay, and all the elements to the right of MA are greater than or equal to the pivot, A of MA, okay? So the next step is to binary search in B to find out where the pivot element A of MA goes. Okay, so we're going to binary search. Okay, you should be familiar with binary search. Okay, and we find that it goes right at that point there. And let's name that place in B where the pivot goes MB. Okay, so all of B's elements from 0 to MB minus 1 are less than or equal to the pivot. And all of B's elements from MB to NB minus 1 are greater than the pivot. Okay, now now MB might be as small as 0, right? And it might be as big as NB. I guess MB has to be at least 1, right? Because if it's 0, then no, okay. Because we're looking at the things between the elements. So yeah, so there's going to be, it's going to go, MB could be as small as 0, and it could be as big as NB. Okay, and so it's going to go in there. We don't know how it is. So we're going to split A in half pretty much equally, but B may be an unbalanced split. Okay, but it's going to be the smaller of the two arrays, the one we split unevenly. Okay, so now we can use our pmerge function to recursively merge those elements below the pivot in A with those elements below the pivot in B. And simultaneously, in parallel, we can use the pmerge routine to recursively merge the elements in the two arrays above the pivot. Okay, so we basically, and that's basically the idea. And why do we have some hope that this is going to work? Well, here's the basic idea. Okay, what we're trying to do is get a reasonably good split, because it turns out divide and conquer works well if you have a pretty good split. It doesn't have to be a perfect split. You don't have to find the median of everything overall. Okay, finding the median of everything overall would take a bit more work. Turns out there are some ways to do it that are reasonably fast, but turns out this is sufficient, just doing a simple binary search. Okay, so suppose that the total number of elements to be merged is n. So n is NA plus NB. Okay, so what's the largest number of elements you could have in either of the two recursive merges? Okay, please suggest your answers in Slack. Okay, what's the largest number of elements that you could have in one of the merges? About 2/3 n, about 3/4 n. An upvote for 3/4 n. Yeah, it's NA over N2 plus NB, but yeah, so basically people are starting to get it, okay? It's got to be at most 3/4 n, okay? So half of A's element, which is at least a quarter of the total, must be involved in each of the two recursive merges, okay? So half of A's elements are involved, and that's going to be at least, whichever way you go, you're going to deal with at least half of A's elements. So the total, and A has got more than half the elements of N, so you've got at least a quarter of the elements. Okay, the smaller one involves at least N over 4, and that leaves the larger one with at most 3N over 4, okay, for the other merge. Okay, is that clear? Good. Okay. Okay. So let's walk quickly through this code. And you'll see this is a pretty simple and easy to code up algorithm. So here's, has the same calling as we've used for the ordinary merge. We call it pmerge. So if NA is less than MB, what we're going to do is swap A and B and call pmerge recursively with A and B swapped, okay? Now, normally, that sounds a little dangerous that we could do. Well, what if we call it and it comes back and it just wants to swap it back? But no, the next time around, NA will be bigger than NB, so we won't keep looping, okay? It'll only do that swap one time, and then it'll go into the rest of the code. Okay, but that's kind of an easy way, rather than trying to write out the two cases and having to recode a lot of stuff. And the extra function call probably doesn't matter that much. Okay, now if NA equals 0, that's the base case, because neither A nor B has any elements, because NA, remember, is the larger of NA and NB. Okay. Now, here's the place that you might want to coarsen the recursion to use the efficient serial algorithm. Okay, so for example, you could check, is NA less than, some number like 10 or 50 or 100 or something like that. You'd have to tune that to find out what's the best number to use there. And at that point, what you might do is just use the efficient serial merge that we gave previously, okay, to handle those base cases instead of letting NA drop all the way to 0. Okay, but for this lecture, I'm going to keep it simple. Okay, we'll just go recurse all the way down, but in practice, you probably don't want to do that. Too much function call overhead. Okay, good. Now, so the next step is to compute the index n over 2 of the pivot, which, as we mentioned, is the median of A, okay? And we can binary search now the pivot A of MA in the array B to find the point where it belongs, which we're calling MB. Okay, I didn't provide the code for binary search, okay, but I presume that that's something you could code up. Although binary search, by the way, is an algorithm which is notorious for having bugs. Okay, people think they wrote it right and they missed a condition. Okay, so in any case, you want to be careful coding binary search. Okay, so after the binary search, we now store the pivot itself in the output array, okay, at the correct point. Now, what's the correct point? Okay, it's MA plus MB, okay, that index, because that's how many elements will be in the lower part of C, because they're going to be MA elements from A and MB elements from B that are, those are the number that are lower than A of M A. Okay, that clear? So that's how many we, so that we know where that goes. You stick that right where it belongs. Okay. And now here's the parallel recursion. So we spawn a pmerge on the lower elements of A and B. Okay, so we go, we merge the A from A0 to A of MA minus 1, okay, because we're doing half open here. And similarly for B, B up to but not including index MB, okay? And we store those in the output array C starting at C0, okay? And then we call a pmerge. We call, the first one we spawn, the second one we call, we could spawn it too. The Silk compiler will actually get rid of it. So if you like it, if you think it's more elegant to spawn off the two things with Silk spawns, it should not have any difference on the optimized code. Okay, so the second one is that we call a pmerge on the upper elements of A and B, okay, and put them after the pivot in the output C. And the way I'm doing that is doing the C array trick. So A is really just a pointer to A0. Okay, so if I do A plus MA plus 1, that ends up being a pointer to the element right after the pivot. Okay, and we're going to say in this case NA minus MA minus 1 elements, because we've got MA elements from the first merge from A, and then we have the element, the pivot itself, that's the minus 1. Okay, and so we end up with NA minus MA minus 1 elements. Okay, now in B, we want to go, we're going to want to put B to advance it, to start B at B plus MB, okay, because there's MB elements lower. And now we have the remaining elements in MB, that's NB minus MB. So notice there's a little bit of difference there between A and B, because A is where we pulled the pivot from. So it has the minus 1, whereas B, we don't have a pivot there. We're just finding a point between two things. So it's NB minus 1. And the number, and we're going to go all the way up to, we're going to start that right after the place that the first one goes. That's, so the first P merge goes from C to C plus MA plus MB. And then we have the pivot, and so the element where we're going to want to put the results of this merge are going to be starting at location C plus MA plus MB plus 1. Okay, so a little bit tricky array indexing calculation, but not too bad. Okay, and that's it. Getting those details right can be tricky for sure. Okay, and it's a really good idea to have unit tests, and throw a bunch of random problems at it and a bunch of degenerate problems at it, etc., rather than just coding it up, sticking it in your merge sort, and then expecting, to debug the whole thing. Always better to do unit tests if you can. Okay, try to find a bug. And if you do find a bug, remember the methodology is you first write tests to detect the presence of the bug. Then you fix the bug, and then you test to make sure that the test is passed. Okay, so you always fix the bug. You always write the test first and make sure that what you've got fails that test. Okay, then you can fix it. Okay, and then you can and then you test to make sure you now pass the test. Okay, and that's how you add things to your regression suite. That's it. Okay, so that's the parallel merge. Okay. So it's not from this abundantly clear what the work of the parallel merge is. We want to analyze the work. Okay. And the place that the algorithm looks dicey is the binary search. That's a logarithmic time overhead. But let's make a guess as to the work in the Slack poll. So let's do a span poll here and have people guess what the work is going to be. Not the span, the work. Okay, log squared n is leading. Okay. Any other thoughts here? Okay. It turns out that the answer is theta n. Okay. So this is work we're talking about here now, okay? And if you do a little bit of a sanity check, the work of parallel merge, you've got n elements. They've all got to make it into the output array. So the work can't be less than n, right? So when you answer quickly, you want to think a little bit about, the answer has to be either theta n or theta n log n or theta log squared n. Okay, it couldn't be theta log squared n or theta log n. Oh, I see. The reason people got confused is because it says what is the span and this is what is the work. Okay.
Charles, you didn't specify a work poll earlier.
Yep. Sorry. Yep, I forgot. Okay, my bad. My bad. Okay, yeah, this is not because you don't understand. This is because I am incompetent. Okay. Yeah, so sorry about that. It says what is the span, and I really meant to ask what is the work. Sorry about that. Okay.
Do you want to put a work poll in right now?
Well, it's too late now. I've told him the answer. So, okay. Okay, well, you know, some days you win, some days you lose. Today, I guess I lose on that one. Okay. I got concerned there, right? So, and I'm trying to explain it. It's like, no, but you're asking the wrong thing. Okay. Okay, so I think we all get this, that it turns out the work is theta n, okay? Now, you might think it might be theta n log n, okay, if you think about the work, because you're doing a binary search, which costs log n, okay? But we want these things to be theta n because that, if it were greater than theta n, our algorithm would not be work efficient. So before we analyze the work, let's talk a little bit about work efficiency. Okay. So is it work efficient or not? Okay, so work efficiency. So the notion of work efficiency is really important. Now, early theories of parallelism worried about how fast programs could run without worrying about the impact on work. What researchers found was that some algorithms could be made to run really fast, okay, in polylogarithmic time, which is a term that means something like order log n or log squared n or log cubed n, you know, a polynomial in the logarithm. So that's polylog. Okay, these researchers realized that you couldn't use exponential resources, that was going to be, you know, too much. But polynomial resources, something like n squared or n cubed, that was okay if you really wanted to make things go fast, okay? And the complexity theorists came up with a complexity class called NC, which consists of the problems that can be solved in polylogarithmic time using a polynomial number of processors. Now, NC is a really interesting class from a computational complexity point of view, because NC is a subset of P, the class of all problems that can be solved in polynomial time, in this case on a single processor. But it's not known whether the subset is proper, that is, whether NC is equal to P. And that turns out to be related to the famous P not equal NP problem, which as a computer scientist you should know about. Okay, and I highly encourage all of you to take a good theory class in complexity theory. Okay, it really gives you good perspective on solving problems, especially in things like AI. But although NC is interesting from a complexity theoretic point of view, okay, it doesn't have much practical bearing on the design of efficient parallel algorithms. And the reason is that a polynomial number of processors is like, hey, usually the number of processors is much less than the size of the input, let alone being polynomial in the input size. So instead, serious parallel programming researchers today tend to focus on how fast they can make work-efficient algorithms run. So what is work efficiency and why does it matter? Okay, so here's the definition. Okay. So let's let T sub S of n, that's for serial, T serial, be the running time of the best serial algorithm on a given input of size n. And now let's let T1 of n be the work of a parallel program, its running time on one processor on the same input. Okay, the work overhead of the program is the worst case ratio lambda of n, which is T1 of n over T serial of n. And that's got to be at least 1, because otherwise your best serial algorithm is to run your parallel algorithm serially. Okay? So that's greater than or equal to 1. Okay? So that we call the work overhead. And we say that the parallel program is work efficient, okay, if T1 of n is approximately T sub s of n. Okay, that is, they're almost the same thing. Okay, typically you write that as Ts of n plus little o of n, or something to that effect. Okay, or plus little o of, it's s of n plus little o of T of s of n, T sub s of n. Okay, and we say that it's asymptotically work efficient if T1 is theta of Ts. Okay, now I personally prefer work efficiency over asymptotic work efficiency, but you can sometimes you can only get asymptotic. Sometimes it's hard to compare constants. Okay, but in a lot of cases, if you make it asymptotically work efficient first, you can engineer by coarsening the recursion and things like that. You can engineer something that for large n is every bit as good as a serial algorithm. Okay, there are lots of them, and Silk makes it easy to do that. Okay, now the other thing that's helpful to know is something called the work first principle. Okay, so let's think about this a little bit. Suppose that the worst case work input for a parallel algorithm on a given input, okay, is lambda, which is T sub s over T sub 1. So I run the serial algorithm, okay. Did I do this right? Oh, I did this wrong. This is the efficiency, not the overhead. It's supposed to be T sub 1 over T sub s. Got it backwards. Okay. It's supposed to be T sub 1 over T sub s. Sorry about that. I'll fix that later. Okay. So the work law says that T sub p is greater than or equal to T sub 1 over p. Okay? And so that is lambda. Yeah, so I've got lambda upside down. Okay? Plugging in for lambda, okay, I have that it's equal to lambda times T sub s over p, where lambda is here the work overhead. I really can't bear looking at this slide. Excuse me for just a minute. I'm going to fix it, and then we'll because I just can't bear it. Okay, I did that wrong. Okay, so let's start that up again. Okay, go back to Zoom. Let's share that. That was a bad mistake. I guess I've made worse. Did I get back? Okay, all corrected. Good, thank you. Okay, so it's T sub 1 over T sub s. Did I do it wrong on the previous slide too? No, I did it right on the previous slide. Okay. Okay, so it's T sub 1 over T sub s. That's the work overhead. Okay, so you can define the work efficiency the other way around as the inverse of the work overhead. I didn't bother to do that because usually you just use the, whether it's work efficient or not. So because of the work law, we have it's T1 over P, and that's equal to that's equal to lambda times T sub s over P. So it's one thing to get great linear speed up relative to a one processor execution. But if the one processor execution of your parallel code is 10 times slower than your good serial algorithm for that, okay, you're not going to get, okay, you're going to have all your speed ups bounded, by 1/10 of what they could be. Okay? So the honest comparison is always with T sub S. Okay? What a lot of people you'll see in the literature do is they compare only with T sub S, and they don't show how it scales with T sub 1, or they'll compare it with T sub 1, and they'll have a terrible algorithm, okay, that doesn't actually, even for any number of practical parallel processors on a parallel machine, will be faster than the best serial algorithm, okay? What you really want to do is understand both of these things, both TS and T1, okay? That's what you're after, because then you can see your work efficiency. And if you can see your work efficiency, you know where to work to make it go fast. It's not because you've run out of parallelism necessarily. It may be the reason you're not getting the good speed up is because you've got too much work overhead. Okay? So some lessons here. Okay. So you can't get near perfect linear speed up over the good serial code no matter how many processors we run on, okay, if lambda is big, okay? I should have said if lambda is big, okay, if the work overhead is big, okay? And in that case, we're simply wasting processor power proportional to the work overhead. Okay, the bigger the work overhead, the more we're just wasting it because you can't get it back. Okay, running it in parallel is all well and good. You may be able to make it run faster, but it's like, if you're at 10% efficient here, okay, so you have a work overhead of 10, then if I run on 10 processors, then I'm back to getting something equivalent to a serial code. Now I can start making progress, but hey, I need 10, to get to 20, I've got to have 20 processors, to get to a factor of 2 and so forth. Okay? So you typically in optimizing parallel code, you have to put work first. Okay? You have to put work first and put parallelism second if you want good performance. Now, there are some applications that are really difficult to parallelize in a work-efficient fashion, but even some of those, you can figure out a way to sacrifice just a few % in work efficiency to obtain good parallelism, and then it may be worthwhile, okay? If I say, okay, well, let me give up 5% for serial execution, okay, that may be okay because now I can, run on 32 cores with no sweat. Okay, so sometimes you can do something like that. Okay, now let's analyze the work of parallel merge. Okay, so we said it was order n, let's see why. So the work, okay, we can analyze by writing a recurrence. What else? Okay, so at each level of recursion, we're going to get a split of merge, of the merge size that ranges between between 1/4 and 3/4. And we have order log n for the binary search and other constant overhead. So that yields this recurrence, okay? 10, and now we're going to, this is a, good. So here's the recurrence, okay? So T1 of alpha n, where alpha is in the range 1/4 to 3/4, plus T1 of 1 minus alpha n, that's whatever left, plus theta log n. It's a little bit actually even more flexible than this because the alphas can change as you go down the tree, but you're always between 1/4 and 3/4, okay? So, so what we'll do in the poll is let's put up a case poll, TAs, not a Slack poll, okay? So a case poll, okay? Which case of the master method is this? Which case the master method for this recurrence? Okay. Okay, so we're getting some thoughts. We got a couple case ones and a few case twos and a few people saying it doesn't apply. What else do we have? Oh, we've got some more coming up. We've got case 1, case 2, case 3, does not apply. Okay, we've got a pretty good spread here. Yeah, this is one the master method does not apply. Okay, master method has to be of the form A T of n over B, and that's not what's going on here. Okay, that's not what's going on. Okay, the master method doesn't apply this type of recurrence, and we have a technical name for recurrences where the master method doesn't apply. Okay, so the shorthand name is, we just call it a hairy recurrence. Okay, so this is a hairy recurrence. Now, whenever you have a hairy recurrence, just because the master method doesn't apply doesn't mean you can't use some other method. You can use Acrobazi or recursion tree or the substitution method to solve the recurrence. Okay, there are a bunch of different ways of handling hairy recurrences. Okay. What I did here is I gave an analysis using a substitution method, which is essentially a proof by induction. And I'm going to let you look at this on your own or learn to solve it in some other way. Okay, you won't have anything that's involved in the quiz. Okay, but you can never learn too much math. Okay, that's something that that I found is generally true. You can, if you're a computer scientist, you can never learn too much math. Okay. Okay, so so it gives you, though, order n result. Okay, so now let's compute the span of merge sort. Okay, so first, and this time we're going to guess. First, let's make a guess in the Slack poll as to the span. Okay, so we'll have a span poll. Yeah, it's true that you could have bounded the work solution using the master theorem, but you wouldn't get a tight bound if you bound both of them by 2 times 3/4 of n. You would not have gotten a very tight bound. Okay, so do we have the Slack poll up? Oh, there it is. Okay, there we go. What's the span? Here we go, log squared n, log n, log squared n log squared n log n. This is for the span now. This is for the span. Log squared n, log n, log squared, okay. Good, okay. So we've got a little divergence between log squared n and log n. Okay, so let's see. So the longest path, we'll get a recurrence. So the longest path in the underlying trace goes through whichever recursive call has more work. Okay, in the worst case, that's a call that operates on 3/4 n elements. And so if we have that situation, then we know that it's at most t of 3/4 n plus log n. Okay. Okay. So the log n is for the binary search and other bookkeeping costs. Okay. And assuming that it's an equality for the upper bound. Okay. So assuming this is equality, what do we get here? So please we'll do another span pole. What's the, sorry, no, not a span pole. We want a case pole here. Which case of the master theorem is correct? Okay. So, case 2, well, it seems like people think case 2 anyway so far. I saw case 3 briefly. Oh, there's case 3. Okay, case 2, k equals 1. Okay, let's see. Okay, so it turns out that C, case 2 with k equals 1 is correct. Okay, and let's just see why. So here, A is 1 and B is 4/3. Okay, because it's n over B. That's the same as n over 4/3. 3/4 of n is n over 4/3. Okay, and so we have n log to the base b of A is n to the log base 4/3 of 1. Well, that's just n to the 0, which is 1. Now, f of n, okay, is log n, which is n to the 0 log n. So we just tack on an extra log n, okay, and we get log squared n. Okay, so let's see. So now we can analyze the parallelism of parallel merge. Okay, so we have work, which is theta n. We have span, which is theta log squared n. And we have parallelism, which is theta of n over log squared n. So for large n, that's not bad. Okay, we have pretty decent parallelism if it's large enough. Okay. Okay, let's look at the work of merge sort now. So we just did merge. Now we want to plug in the work, which is theta n for p merge, and the span, which is theta of log squared n, into a recurrence to solve for the work of parallel merge sort. Okay, so here's the recurrence. Okay, so we have in merge sort, we have 2 problems of size n over 2. Okay, plus the work of p merge, okay, which is order n. Okay, and that's the same as the analysis for the original serial merge sort, as well as for the first parallelization of merge sort. So we're not going to bother with the pole. Okay, the answer is going to be, of course, case 2 and theta n log n. Okay, and that means that parallel merge sort is asymptotically work efficient. Okay, and as a practical matter, you can get it to be pretty efficient if you pretty close to the time of an ordinary merge sort by coarsening the recursion. Okay, so now the span. So let's first guess in a slack pole. What's the span of parallel merge sort? Log cubed n, log squared n, they seem to be battling it out. Log squared n is trying to come from behind. Whoa, it's neck and neck. Vote if you haven't voted. This is close. This is the closest one we've had. Go, 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 go. Oh my goodness. It's close. And they're coming around the bend into the stretch. It's log squared n by a nose. But log cubed n is bringing it. Oh, log cubed n has brought up from the rear. We're getting close to the finish line, and it is log squared n by a nose. But the answer is, we'll see. So here's the recurrence. Okay, we have t of n is t infinity of n is t infinity of n over 2, because we're solving a problem of half the size. Only have to do one of the worst case. And the span, remember, of the merge is theta log squared n. Okay, so which case is this of the master theorem? So let's do a slack poll for the case. That'll be our last poll. Yeah, so this, I think, people are doing well on. Okay, so this is indeed indeed case 2. Okay, with a equals 1 and b is 2, so we have the same thing we had before, which is n to the 0, but f of n is now log squared n. So we tack on an extra log, and we get log cubed n. Span is log cubed n. Okay. So when I look at the parallelism, it's just the ratio of these two things, and so we get a merge sort with parallelism theta of log squared n. And as I mentioned, by coursing the base case, this algorithm is pretty good in practice. And in fact, with a bit more cleverness, the parallelism bound can actually be improved to n over log n without sacrificing the asymptotic work efficiency, although the work overhead is a bit larger. Okay, so that's basically it. You can see how recurrences can really give you, and an understanding of the master theorem can really give you some insight into how these algorithms work. And you will definitely see some algorithmic work on the quiz in 2 weeks. And that's the end of the lecture. And I'll hang around once again for anybody who wants to chat. I hope some people will chat this time. We had a few people last time. Okay, we're having a good time after class. You should see I'm giving people answers to quiz questions and telling them things that give them huge speed ups on their project code, so hang around, and lots of life advice, okay, of how you can be successful in life, engineer a good life. Okay. Yeah, no, nobody likes unsolicited advice, really. Okay, let me end the